Okay, so we're going to prepare solutions two ways. We're going to prepare them from a solid, like taking a solid and dissolving it in water. And then we're also going to dilute a solution. So if you have a solution that's very concentrated and then you want to make it less concentrated or more dilute. So a standard or stock solution is a solution with an accurately known concentration. When we get to acids and bases, we'll look at a lab procedure where you can really accurately measure volumes added to another solution and use that to figure out your unknown concentration. So this is more like preparing a standard or stock solution that you know the concentration of. Grade 10 teachers come and say to me, I need iron chloride solution for my lab. Okay, what concentration do you want? 0.5 molar. Okay, and then I can do the math to figure out how much solid to dissolve. And of course, we're always using distilled water to measure to make the solution. So as always, mass needs to be converted into moles. So you can use whether you like the equation or the formula from before. So mass over molar mass gives you moles. So then mass is multiplying. But normally we don't store the solutions, or we don't think about the solutions just in terms of moles anymore. So now we're going to think of them, what is the concentration, which is moles per liter. So then you need this formula from yesterday as well in order to change concentration and volume into moles. So you can do this as 2 steps because there is a common variable, or you can use one big formula. So if I rearrange this, so moles is C times V. So you can sub it in. So wherever there's moles, we're going to sub this into there. So I'm going to put C times V times MW. I'm just going to go in the same order. When you multiply, it doesn't really matter what order you do it in, right? So I took this original change mass into moles formula and rearranged it to solve for mass, then rearranged concentration to solve for moles, and then you've got a common variable and you can sub it in. If you are a triangle person, you can do triangle if you prefer. Yesterday, when we did molar concentration, volume had to be liters. So the same thing applies today if you want to write it on today's note as well. But really, technically, none of these formulas are new. We're just sort of manipulating them and using them differently. So if you would rather not think of a new formula, you can do the question into more than one step and sort of just go through and write down what you're given, what you're looking for, and just kind of sequentially find it, you can do that too, okay? So when we do the example, I'll show you both ways. And so this you already know, molecular weight, where do we find that, or molar mass? The periodic table. Mass has to be in grams. All the same principles like from unit 3 still apply. And then this, of course, is from yesterday, moles per liter, okay? So how much potassium iodide is required to make 250 milliliters of a standard solution of 0.5 mole per liter Ki? So this is supposed to be an I. If that bugs you, you want to fix it, make it look capital. So you need to know what solid you're doing. And then now we have concentration, mass, volume, and molecular weight. So there are 4 variables. So again, you kind of need at least 3 of them. So you're given 2, and then just like before, it looks like you're not given enough information, but you can find molar mass. So if you got to the point where you were just like, okay, it's just K plus I, and all you had to do was write down the molar mass, that's fine. You can continue to do the same thing. What I'll do is I'll show as much work as possible so that you have, when you go back and look, you've got it all there, okay? So we want to, we have potassium iodide. You could change the volume into liters first. It doesn't really matter. Okay, so again, if the molecular weight, you even just put it in the calculation, that's okay. We need volume is 250 milliliters. Has to be liters. So again, if I give it to you milliliters and you have to change it into liters, that'll be worth a mark. So it's worth your while. So again, maybe you can, or you know that you're just moving the decimal place 3 spots. That's fine. You can just write the answer. Maybe you want to show your work. It's kind of up to you, okay? Changing milliliters to liters is going to be something that we do often in both this class and grade 12. And then we're given concentration. Okay, so if you want to do it using, I'm just going to go back for a second. If you want to do it using this, you can. And then what I'll do is kind of split my page. You guys have lots of space there. And I'll do it with this, and then I'll do it the 2-step way. So big C, we already wrote it down, concentration. When you're given the units of concentration, moles per liter, even if you forget that volume has to be in liters, this hopefully will be your reminder. The unit is moles per liter. And then we already found the molecular weight or molar mass. Yep, sorry. Thank you. I wrote it up there, right? Yes, okay. Okay, so now if you are a dimensional analysis kind of person, so now liter in the bottom, liter in the top, they cancel. Mole in the top, mole in the bottom, they cancel. And we're left with grams, which is what we want. Or you can do it in a two-step way. So concentration and volume can be used to find moles. So you multiply. Okay, and then when you make these solutions, our scales don't read moles, so we have to change it back into mass. I'm running a room, so again, you're going to multiply, and you get the same thing. Okay, so you decide what you would prefer. So now to make this solution or to prepare the solution, I would take 20.75 grams of potassium iodide or Ki and dissolve it in 250 milliliters of water. So if you're going to make an aqueous solution, by definition, what that means is the solid is going to dissociate and fit in between the water particles. The water volume should not change. So we're not talking about, having a teeny bit of water and just like dumping a huge amount of salt in it. We want to make our solution clear. So we want it to dissolve, okay? When we do dilution, we're going to have, and you're adding water to make a solution less concentrated, you're already going to have an aqueous solution amount and you're adding more to it. So there is a little bit of a difference there when you're actually going to make the solution. So when you guys do the lab today, you're going to do both. You're going to dissolve a solid in water and you're going to do dilutions as well, okay? So let's just make a little note of that. Okay. So what happens when you already have a solution? So this is a new formula, but also on the formula sheet. Sometimes you might see this as CIVI and CF and VF. So I being initial and F being final. So 1 comes before 2. So that means the one side here is the more concentrated solution. Or initial if you prefer. And then 2 is the less concentrated or final. So as soon as the question says you have a solution of this concentration, we want to dilute it to something else. As soon as you see the word dilute, then you're going to use C1V1 equals C2V2. So this is a really common formula to use, even when your lab isn't really about doing dilutions. Often next year in university, you'll get a really concentrated initial or stock solution, and then you have to make your own little solutions in order to do your lab, okay? So you could be doing a lab that's trying to make copper or doing something with acids and bases, but the first step is you need to make a series of dilutions. So you'll have to do this even though it's not really testing you on the dilution part of it. You just need to make your own solutions. So you have to kind of think of it logically. The math here is really straightforward. Sometimes students mess up because there are 2 C's, 2 concentrations and 2 volumes. They put the wrong numbers together, okay? So you're adding water to a concentrated solution to make it less concentrated or more dilute. You can't quantitatively have a really dilute solution with lots of water and evaporate the water and expect to get a specific concentration back. Yes, you can evaporate water, but we want to quantitatively know how much solute is dissolved in the solvent. So then logically, it makes more sense. I have something really concentrated. I take a little bit of it out. I add it to water to make a final solution. That makes way more sense quantitatively, accurately, precisely. Okay? We're going to use graduated cylinders today to make our solutions. You could even get more accurate apparatus called pipettes. So we normally just use those little plastic ones that are about 1 milliliter, not very good, but you can get really graduated pipettes that have lots of calibrations to them. In biology, you might have even used micropipettes, which are super, super, super tiny amount, because obviously in bio we sometimes deal with micro amounts. But today we're just going to use a graduated cylinder. So when you make measurements, especially when you're doing something like this, you should definitely not use the beaker, okay? So the beakers are just there to be your vessels to hold your solutions. Their calibrations have, I think ours have 5% error. That's way, way too much, okay? So you have a big graduated cylinder at every station and also a little one, okay? So then you have some options to do both. I can even give you a little pipette to put in the graduated cylinder if you prefer, but you don't want to use the beaker when you're measuring your solutions. So we're not going to take water out of the diluted solution to make it more concentrated. We're going to take a little bit of the stock solution, put it in distilled water to make it less concentrated. It doesn't really matter. This is an equal sign. It doesn't really matter which you put first, but it does have to go together. So the information for the more concentrated solution goes together, and the information for the less concentrated solution goes together. So what volume of 3 molar sodium hydroxide would be required to make 250 milliliters of a 0.15 molar solution? So this concentration, the 0.15, is obviously much, much less than the 3. So how much of the 3 are we going to take out to make the other concentrated solution, or the less concentrated solution? So if you are the kind of person and you like to write out your data, that's great. But you can, again, sort of think of the logic of what's happening here. So we're going to make 250 milliliters of a solution that's way less concentrated than 3. So that means the amount, and we usually use volumes because it's already like a solution liquid, then we are not going to need very much of the 3 molar to make it way, way, way less concentrated. Sometimes it's not such a drastic change. 3 molar sodium hydroxide is pretty concentrated. Sometimes it's like 1 and 0.5, but on a paper and pencil task, then the greater the difference in the concentration, then maybe the easier it is for you to see how logical is my answer. Okay? So I'll write out the data, but again, you can sort of reason through it if you don't want to do that. So what volume of 3 molar sodium hydroxide So what volume, that's what I'm finding. So even if you don't put 1s and 2s, as long as you know, okay, I'm trying to find how much of the 3 molar I'm going to use when I'm trying to make less. Less concentrated, more volume. So even that can sometimes be a little bit weird, but if you think about it logically, if I have more water, then it's going to be less concentrated. So same thing, change it into liters, showing your work or not. Maybe you're going to be used to this. Same thing as before, you need to have 3 out of the 4 variables. You can choose to rearrange the formula first or plug in the numbers and then rearrange. It's kind of up to you. So you're going to do 0.15 times 0.25 divided by 3. And you should get 0.0125 liters. So we've answered A, okay? If this was a paper and pencil task, this question would be out of like 2 or 3, pretty straightforward. So it kind of depends on the question. When we do the lab, we are going to actually prepare the solution, but technically, in this question, that is really part B, okay? So how would you prepare the solution? First of all, unfortunately, we use liters in our calculations. However, our graduated cylinders do not measure liters. So if you have to talk about what happens in the lab, or if you had to actually go and make this, which, again, test, quiz, whatever, you don't. But here we need to make this solution. So that means that we need to change this back into milliliters. Okay, so when you're diluting a solution, you already have some milliliters. Yes, 250 milliliters is much more than 12.5, but still, if you put 12.5, or sorry, if you put 250 milliliters of water and then add 12.5 milliliters to it, you are going to noticeably change the volume. So when you dilute a solution, you know what you want the final volume to be. You already have some volume. So then the amount of water is actually that you're going to use is actually the difference between them. Sorry that I had to squish. So unlike the other solution where we took a solid and dissolved it in water and the volume didn't change, now that we have 12.5 milliliters of solution, then you need the difference between them for the amount of water so that your final volume is 250. So sometimes what people will do is actually have the graduated cylinder, put the 12.5 in first, and then go up to 250 in the lab to make sure that you're not making your solution have a greater dilution because you've added too much water. So there is a tiny little difference there. So the homework is broken into two. There's solid questions and then there are dilution questions. So again, make sure you're looking at both. But right now, once you get this down, I want to take a look at the lab worksheet. So that's the one with this on it.